for question 26, again, you have to use the V equals to F lambda equation. So the only distractor they have here is that the distance, the sound wave, the wavelength given in the question is in cm, but when you are using the equation, you have to make sure everything is back to SI unit. So speed, it is already in meter per second, so you need to change the lambda back into meter form. So once you have that, you know the upper limit is actually 300 kilohertz. Okay, and you know that anything lower than that, lower than 300 hertz, like for example 15K, it can be heard by human beings. So therefore, the only option that that is above our hearing range is this option D. Okay, question 27. Question 27, it is pretty straightforward. You are given the angle of incidence, you are given the angle of refraction, you are told that it is going in from air to an optically denser medium. So meaning that you can simply use this version of the Snell's law, n equals to sin over sin r. You substitute the angles in, you'll be able to find out the refractive index of water, which in this case is 1.22. So when you are asked to find the speed of light in water, you can use the definition of refractive index, n equals to c over v. Since you have already find n here, you can put in the value. C is given, put in the value, then solve the equation, you'll be able to find the answer. Question 28 requires you to understand, have a good understanding of mathematics. So a normal straight line equation would have the form of y equals to mx plus c. Okay, but since we know that when wavelength is 0, frequency will be 0, we know that it is not going to have a y-intercept. So you know that generally, if you have a graph like that, a graph like that, or a graph like that, it will fit into y equals to mx plus c. So if you look at the wave equation, v equals to f lambda, there is no c component, so most likely c is actually equals to 0. That's why it will be simplified to this kind of equation. Now, since the frequency is on the y-axis, and if you look at the standard straight line formula, y is on the left, like as a subject matter. So what I want to do now is I want to make f my subject. That means I want f on one side alone, just like this case when you have y alone on one side. So in this case, I will have to move my lambda over, and I divide by lambda both sides, so that's why I get this. Now, if you look at this, and you compare with this form, the f is where the y-axis is, and the x-axis actually must take the value of 1 over lambda, not lambda. Right? If you have lambda here, you won't be able to get a straight line, because then the gradient here will not be a constant. Okay, so unless you are drawing a graph of f versus 1 over lambda, then you would have this gradient which actually represents the velocity. So since this case all 4 options, right, is f versus lambda, you know that it won't be a straight line. Just look at this equation, you won't get a straight line. So therefore, the only option that is accurate would be A. Okay, your question 29. Question 29, you need to recognize that when your angle of refraction is 90 degrees, meaning that when the light comes out from optically denser media and it is running along the boundary, this angle here is actually the critical angle. Anything that is larger than this critical, your light will be trapped inside this medium and you have total internal reflection. So use geometry. This is 90. So this angle will be 90 minus 43. So this angle will be 90 minus 90 minus 43. So therefore you will get 43. Yeah, this will be 43. So since you know that this configuration of rays is actually saying that this angle is my critical angle. So use your critical angle formula, substitute 43 inside, you will get the refractive index. Okay, question 30. Question 30, you are given the focal length and you was told that you want to have a magnified image. The only way to do that is when the object is placed within 1f. So it must be lower than the focal length. So option A.